Sorry I haven't made a video in a while. I've been working on the Super NT that's been dominating all my time up until now. So I got a special treat. It is a versus Super Mario Brothers board, but it's unlike any of I've ever seen. It's actually a pirate board here, and what they've done is they've took the usual CPU and PPU chips and they've redone it all with a Z80 and a regular 6502 and a whole crap of logic. So there's about 170 chips on this board, and I've actually drawn a schematic out and reverse engineered this thing. Why? Because it was fun. So let's get to it. So here's the board. When I got it, it was just a board, and then I had the mystery harness here. And this mystery harness, it had this connector on the end. I don't know what it was for. It wasn't JAMA, because if it was JAMA, I wouldn't have cut it off, but it's not JAMA, and I have no clue what this is for. So it's probably for some random 80s arcade cabinet. So I liberated the end of the harness and made this adapter. So this plugs into a modified controller. So this controller here outputs all the buttons separately on this ribbon cable, and that's just plugged in here. And then this is a 15-pin connector that plugs into my RGB cable. So I just plug that in here, and that connects it to the PVM. And of course I got this controller so I can actually put money in and play it. And then it's just connected up to the power supply to run it. I've just got the 5 and ground on there. I'll hook the audio up in a little bit, but man, this thing draws a lot of power. It's over 3 amps. So I just got an old computer speaker here. It's just a speaker, there's no amplifier in it. So I'll plug this cable in there. And then I've got an 1/8 inch end, and I'll just get some clip leads here. There, so I got the 12 volts hooked up, but just to be safe, I'm going to hook or test it. I always like to test this stuff with the meter. I mean, it seems kind of silly because I'm pretty sure it is right, but I mean, it never hurts to check and check again. So this should be ground. It is, and then this should be 12 volts, which goes to pin 5 of that audio amp. And it is, and it goes to this diode too. Yep, so it's hooked up right. This ghetto fabulous setup with 2 clip leads hooked up to this audio cable. Get my controller out of the way here. And I got this speaker hooked up to that cable, so I'll put that over here. And I'm going to set, so I'm going to set the current down to like 100 mils here. Yeah, I know. 200 mils. We'll set it to, say, 9 volts. We don't need the full 12. There. And when I turn it on, we should have audio. Wow, there is a lot of noise in that audio. This is the volume pot right here. Let me put some money in. Okay, yeah, that'll be fine. Man, there sure is a lot of noise on that. That's hilarious. Well, here it is running. Sorry about that flicker. There's nothing I can do. I tried changing the settings and there's not a lot I can do. So, sorry about that. Anyways, I'll put some money in here. Now I'll hit the start button. So, it's funny because it looks... That audio is just hilarious. It's really hard. This controller's kind of crap. You have to press like the directions like super hard. And, oh, that's horrible. Oh, that is so funny. Colors are all wrong. One thing I think is funny, when you go to the edge of the screen, the sprites get cut off. It cuts the full 8 pixels of that sprite off right there. When you get to the right side, those Goombas there, Oh, it went too far. It cuts them off too. Oh man, that's hilarious. Oh, that's so funny. The reason the audio is so funny is because there's a Z80 emulating the NES channels. Oh man, it's so funny. Yeah, that is so funny. That is just so terrible. This runs slower also. It only runs at 56 frames a second. So it makes your timing off. So anyways, that's how it plays and how it sounds, which is pretty hilarious. So what I find interesting about this board, there's several things. One is there's a Z80 right here, and this Z80 is emulating the NES audio channels. That's why it sounds so funny. There's dual 76489s, SN76489s. One does the two squares in the noise channel, and the other is just triangle. And they low pass filter with an RC to make it more triangle-like, and they clock it lower too. And so the Z80 captures all writes to 4000 to 4000F, which is where the audio registers live. And when the 6502 writes to it, it actually pauses the 6502, reads what value and address it wrote, and then starts it back up again. I thought that was kind of a cute trick. And then it does whatever it has to do to emulate the audio poorly. But it's funny, they kind of try to do the pitch sweeps and stuff, but it doesn't really work very well, as you can hear. There's also 7 PAL chips, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. Then there's this Altera part. It's an EP1200. This was Altera's second product ever. It's a 24 or 28 macro cell, like a CPLD. I'm not sure if it's 24 or 28. I can't actually find a data sheet for it. Some places said it was 28, but in a patent for that chip, it shows just 24 macro cells. So I'm kind of inclined to believe that. And then there's a 6502, just a stock one, running, the game code. And then there's 5 EEPROMs. This one's got the Z80, like, NES audio emulator. This has the tile graphics. This has the sprite graphics. This is that EP1200. This has the program ROM, and then this has the second bank of character graphics, which the CPU reads to do like the title screen, and then the super player '*S high score screen. And then there's also a dip switch for the settings, like on the regular one. Yeah. Super player '*S, that just really bugs me. Everything runs off a 16 megahertz crystal. That's the only crystal on there. It doesn't run at the usual 21.47. So what they've done is they divide this by 3, and then they get a 5.333 megahertz for the pixel clock, which is actually really close. The regular pixel clock's like 5.32, so this is actually very close. So I was kind of interested in that, because the video, if that wasn't close, the video would be way too wide or way too narrow, and it looks fine. However, they're sending out 280 scan lines, which is way too many. So it ends up being about a 56 frames per second, which is kind of slow. But, I mean, that's just how it works. So let's dive into the schematic. And here's the schematic. So I'll start with the audio since that's pretty easy. So it's basically, there's a Z80 right here. And then there's the 8K EEPROM, there's a 2K SRAM. And then here's there's the two SN76489s. But there's an op amp, and then there's the audio amp chip, and then right out to the speaker. So nothing too big. So they run the one at 2 megahertz for the triangle, and there's the RC low pass, and they run this at 4 megahertz for the squares and the noise. And then they latch the data and the control signals from the Z80 because this chip is really slow. There's this is the hardware that latches the data from the 6502. So it latches the 8 data lines and then the lower 4 address lines, 0 through 3. And then, so when the sound write goes low and it's an I/O write from the 6502, it latches those two things. So the next page is just input. So this is very similar to a Versus board or an NES. It's got 2 4-bit shift registers, which are for the controller ports, like usual. And then there's the other one for the other player, which actually isn't used on this game. And then there's some 7.4 LS240s, which is similar to the chip on the NES that reads the controllers. And there's the dip switches that are hooked up to some of those bits. And it actually decodes 4016 and 4017 using some 139s and some other logic. And then there's this coin counter output that it pulses low each time you put a coin in. And that's decoded at 4030 to 43F for a write. And then we got the 6502, so there's our 16 megahertz clock that runs the show. And then there's this first PAL, and this is a divider. It outputs a 4 megahertz signal at 75% duty cycle, which is used by the 6502 logic to pulse some things. There's a 2 megahertz 50% duty cycle, which is used by the Z80 and the 6502 and one of the sound chips. Then there's a 4 megahertz 50% duty, which is used by just the other sound chip. Then there's various inverted versions of the 2 megahertz. There's a buffered and an inverted buffered version. So then there's the first decoder. This decodes 0 to FFF for the RAM, and then 2000 to 2 FFF, 4000 to 4 FFF, and 6000 to 6 FFFF. And they map in a 2K RAM at 0 to FFF and another one at 6000 to FFF. And the 2 RAM chips are here and here. Then here's that 32K EEPROM, which is just mapped, and they just inverted A15, so it's always on from 8000 to FFFF. Here's the 6502 itself, and then they inverted like read-write and then M2. No big deal. And then this also has the PPU registers, so they have the 2006 registers for the pointer for where you read and write data in PPU memory. They got 2005, but just one of them, which is the X scroll. This does not do Y scroll. And then there's the 2000 register, which is one of the PPU control registers. And then there's the 2002 register, which is like the PPU status, and only 1 bit is like hooked up there, which is kind of funny. Here there's only just the 3. This one turns the NMIs on and off. This one increments by 1 or 32. And then this one selects which name table to show. Very similar to a real PPU. And so then the next one will be the tile rendering engine. So this is where things get a little complicated. I'm not going to go over it really carefully. If you really want to see, you can check out the link for the schematic. But basically the way it works, it's actually really interesting. I'll kind of start at the name table RAM here. This holds which tiles are going to be displayed and also the attributes, which is like which palette to use. And this goes through just a latch, and then it goes through the 8K tile data EEPROM, and the lower 3 address lines are just connected to the Y counter, the 3 bits of Y count, because this shows the the 8 scan lines of the tile for every tile on the screen, and that's how they do it. Then this 4th bit here, bit A3, is actually which tile plane, and then these other 8 bits is which tile to show. and then the tile data comes out, and there's two latches because it's a two tile plane. So this is the tile plane 0, this is the tile plane 1. And then this is two 8-bit shift registers. So this serializes the tile data into the 2 bits here and here, which is the pixel that it's going to show. And then they deserialize it with another shift register, but what they're actually doing is they're delaying these pixels by 1 through 8 clocks. And then there's a 8-to-1 multiplexer selecting one of those. So what that lets them do is see the three lower bits of the X scroll register are hooked up here. So what this lets them do is actually adjust which pixel of the tile is going to be shown. So this is how they do the fine scrolling. So if you select the first output, it's going to show, so if this is the first tile and you select the first output, it's going to show the entire tile. But if you select the next bit, it's only going to show 7 bits of the tile, or 7 pixels, and then 6, 5, 4, 3, 2, and then 1 pixel of the first tile. So that's how the scrolling is done. So that was kind of neat. So then tile 0 and 1 is the final pixel for the tile. And that's how they do it. And then down here, there's a quad 2-to-1 multiplexer, and this is actually how the attribute table is read. So it's hooked up to, like D0 and D1, and then D2 and 3, 4, 5, and then 6 and 7. So this chooses the 2 bits out of the attribute byte, and those 2 bits come out here and here. And then this latches the data, this latches the data, and this latches it. So these are like a delay line. And the reason for this is because it takes time for the data to go from the EEPROM to these latches, to these shift registers, to these shift registers, and then into the selector. So you got all these clocks that it takes to do that. So they delay the attribute bits, which is basically 2 more pixel bits. So the pixel ends up being 4 bits. It's tile 0 and 1, which is the pixel, and 2 and 3, which is the pallet number. But you have a problem if you're scrolling. The seam where you change between attributes actually changes with the tile. So if you don't do it right, your attributes are going to stay the same while your tiles are scrolling, so it's going to look like very funny. So to fix that, they have a counter here. Let's see, where is that? Yeah, or sorry, they have an adder. So this part right here, this is a 4-bit adder. So it adds the X scroll bits and the X count bits, and it adds them together. So when all of these outputs are high, all 3 outputs are high, then this goes low, and that will pass this pixel clock through for 1 clock, and that will latch the name tables. So this is how it controls the tile seam, as I call it. So I thought that was actually really neat. And then they carry a set, so they actually add 1. And then to do the actual X scrolling, they take the X pixel counter, bits 3, 4, 5, and 6, and they add them, or 5, 6, 7, and 8, and they add them to the X scroll registers 3, 4, 5, 6, and 7, and then the name table select, which is that PPU control bit 0. And so what this ends up doing is this selects, as you scroll, it selects the proper tile here with these adders, and then these multiplexers select the correct pixel from the tile to start at. So that's how you can get single pixel scrolling, and that PPU actually works extremely similar to this internally, which so I thought was really cool seeing a TTL implementation of it. So this does not do Y scrolling. They would have had to have another adder on these Y count lines, and they obviously don't have it. So it would have been very similar to this circuit. So then they have this thing. This is a 4-bit counter, a 161. What this does, this counts tiles, and this is where it splits the screen for the status bar on the game. It's actually in hardware, and I call it X page. So this is the only bit that's piped back through register 2002, and it's the Sprite 0 hit. So they're simulating the Sprite 0 hit on the game, which causes it to split the screen, but they're cheating and just counting tiles. So this is preset to 1, 1, and 1, so 8, 9, 8. This is preset to a B hex. I actually said 4, but it's actually B. And then so every tile, this is incremented. So after 4 tiles, this line goes high, and it splits the screen. So that's how they do it. So I thought that was pretty clever. So then, we got our, I've already described the name table ROM, and here's that extra 8K EEPROM that the CPU reads. So this doesn't actually have graphics in it. The CPU just reads this because this holds the title screen data and the super player apostrophe S data and all of that and some code. So that's actually stored in here. So the CPU actually reads this back through this interface. And then there's and then you've got 1, 2, 3, 4, 5, 6, 4-to-1 multiplexers. So what these do, these select either the name table, to figure out which tile to display, the attribute table for which palette to display, or the 6502 can read and write it. And then you've got 1, 2, 3, 4, 5 4-bit counters here, and these are what actually you load your address you want to read or write into, and they increment after you read or write. Then there's some logic here to actually do the 1 + 1 or the plus 32. So they use a counter with a single bit here, which I thought was kind of funny, because this would be 4 bits is 16, and 1 more bit it would be 32. So what they do is they either use this bit here and then the clock in to generate the carry. So every 32 counts, it will actually increment this UN5 here. And so if this bit here is set, it won't increment up here, and it'll just increment UN5 by itself, so that'll effectively add 32. So I thought that was kind of cute. And then the other thing they've done is they actually preload this whenever you change addresses that you're writing to, which I thought was kind of funny. It's kind of like a hack. They probably didn't quite understand how it worked, so that was kind of a hack they did. So then the next thing would be the Sprite Engine here. So the Sprite Engine actually isn't as complicated as I was expecting, but it was kind of weirder. So there's no less than 3 pals here. These are actually the frame timing pals. So you got your 533 megahertz pixel clock coming in, and then this divides it by 336 and generates an X count 0 through 8, which counts from 0 to 335 and resets. So when it resets, it increments the Y, which is your scan line number, and that counts up to 280. And when that hits, 279, it resets back to 0. So that's how that works. And it also generates the V blank, H sync, and the composite sync. The composite sync runs to the monitor, of course. And then here's that EP1200. This is the only thing I really didn't reverse engineer because there really wasn't a need. I still may do it, but I mean it's pretty straightforward, so I really didn't bother. So anyways, here's how it works. This is the EEPROM that contains the sprites, and what they have done is they've actually unrolled the sprites. So every location on this EEPROM is 1 pixel. So these lower 2 bits is actually the sprite pixel here. And then they got some Xor gates, and what these do, this is how it does the X flip and the Y flip. And here's the X flip and the Y flip signals. So it just inverts the 3 X counts, or the X coordinate or the Y coordinate. And they actually, it takes 2 scan lines to update a sprite on this. So, X count 1, 2, and 3 would be your X, and then X count 5, 6, and then Y count 0 is your Y. So I kind of have to explain a little bit. On a regular NES PPU, it renders the sprites as it draws a screen. It fetches them in H blank. That's way too complicated to do in TTL logic. So what they've done is they have a frame buffer, and they render the sprites into this frame buffer up to 64 sprites, and then they display that frame buffer on the next frame, and then they are loading a second frame buffer. So this actually has 2 frame buffers, and it loads one while it displays and clears the other. So I mean, that's kind of obscene, but that's how it works. And then so this is the Sprite OAM. This is where your X and Y coordinates, tile number, and all of that goes. It goes in this little RAM, and the 6502 can read and write it. And what I found interesting is it's actually multiplex. So the 6502 can actually read and write this at the same time the Sprite Engine is using it, and it just uses the 2 megahertz signal to determine if the 6502 gets it or if the renderer gets it. So I thought that was kind of neat. So let's just buffer it. This selects who controls the address lines, either the 6502 or the rendering engine gets to control it. And they use the Y count registers to select which data to output. Then there's just some logic to let the 6502 read and write it. Then these are the latches. So this latch is the X and Y coordinate, and then this goes into that EP1200. And this is the tile number, which is just run right to the address lines to select which tile. And then this is the attributes, which is the X flip, the Y flip, the priority bit, and the 2 pallet bits. So the 2 pallet bits and these 2 pixel bits give you your 4-bit sprite, palette entry. And then this is the priority bit, which determines if the sprites are going to be on top or under the background. So moving on to the frame buffer here. So this has 10 64K by 1 DRAM. So there's 5 here and 5 here. There's 5 because that gives you your 4 sprite pixels, your two pixels, your 2 palette entries, and then your priority bit. That's why there's 10 of them in 2 groups of 5. And so what they've done is they've got these Nand Gates on here, and what these do, when it's reading back pixels and displaying them, it's actually clearing the buffer at the same time. It pulls this line low, and it loads 1s into every single location. And it's inverted, and I'll get to that in a minute. And then there's this flip-flop. This flips and flops every frame, so that means on one frame, these top ones are being written to, and these are being read, and then the next frame, these are being written to, and these are being read. And that's how it does it. There's this flip-flop that selects. And then the data is coming out, B0, 1, 2, 3, 4, 5, and then 6 through 9. And then there's these 2-to-1 multiplexers here that are taking those pixels from the 2 buffers, multiplexing them down to 1 using that ever-present select line here. And then these 3 signals and these are your 2 pixel bits, your 2 palette bits, and your priority bit. And then you've got these 2 chips here, which are 16 by 4-bit RAM chips. They're very small RAM chips. There's 2 of them, and they're running right off of the X count signals here. So what these are doing, these are delaying the sprite pixels by 16 pixels on the screen. And this lines the sprites up with the tiles. And then finally we got our final latch. This just synchronizes the pixels to the pixel clock. And this gives you, your 2 sprite bits, your 2 palette bits, and your priority. So this is the final sprite output, and that's how it's generated. And so to write the pixels into the buffer, the buff in 0, 1, 2, 3, and 4, that comes off the sprite render, and that's the 2 pixel, the 2 attributes, or the 2 palettes, and then the priority bit. And those go into here and here. So here's your buff 0, 1, 2, 3, 4, 5, and then they come in 0, 1, 2, 3, 4, 5. And then these are inverted. This inverts the pixel data, and then these RAM chips have inverted outputs. So these uninvert the pixels. So that's kind of weird, but that's how it works. So that was kind of clever because these RAM chips invert. So we'll just invert the data going in. So when these are, outputting, when this is erasing, so this is outputting 1s, so then this gets back converted into a 0. So that's how they do that. And then there's another PAL here, and all this PAL does, this just runs this little state machine that just, does the RAM, fetch patterns to do this frame buffer. Then on the left side here we got our multiplexers. So it multiplexes between the, I call them the D-add pins for DRAM address. So there's 8 of those. I'll get into those in a minute. And then there's yet more multiplexers. And then these select the X and Y coordinates from that EP1200 is what these are doing. This is the X and Y coordinates that chip generates. And then, so these D address lines, what these do, these come from these 2 PALs and then these 2 adders. And what these adders are doing, they're taking 6 away from X count. because that lines the sprites up on the screen, and that's part of the reason why the edges of the sprites are cut off. I showed on the video, and that's why. So you basically, this multiplexes 3 sources: this X count, the Y count, and then this other X count, which is actually they're using, and this Y count, they're usually using this as a refresh counter. So they actually refresh all of these DRAMs every 16 scan lines. And then this X count 8 del, this goes high when, after it renders 256 pixels, when it's an H length, this goes high. And then this forces these multiplexers to the D address lines, so it can actually tell it to refresh. That's how that works. So that was actually really pretty neat to actually see how they did that. And they're really hitting these RAMs. They're accessing them at the full pixel rate at 5.33 megahertz. So these RAMs are just being pounded, and they're in they just open the row and they just read all the entire row out, and then they erase it at the same time. So that was pretty tricky and interesting of them. Then there's another little multiplexer. This multiplexes the RAM's CAS, RAS, and read-write signals between reading and writing. So when it's reading, you got the CAS and the RAS and the read W coming from our little state machine, and then the RAS signals actually come from here, so they're multiplexing them in here. So you either got this signal here, which goes all the way over here. This is the write signal from the EP1200, so that actually writes the pixels in. Or you got this signal here, or sorry, it generates it internally. It uses this signal to figure out who gets the buffer, because that's again our signal off of this flip-flop. And then that outputs RAS 0 and 1 to the 2 banks. And then so this logic here is from the EP1200, and it's a really big mess. And this is actually what forces the writing to occur. I didn't actually fully work it out, but what it appears to do, looking at the scope, it actually writes 4 scan lines worth of sprite pixels into the buffer every scan line. So it takes 2 scan lines to render a sprite into this buffer. So what this means that the sprites are actually delayed a frame from the tiles, and when I was playing the game, when it was scrolling, after I hit a question mark block and the screen was scrolling, the block actually is pushed to the right into the tiles, and that is because it's delayed. So the tiles have already scrolled, but the sprites are haven't yet, so they get pushed in there. And I'll show a little clip of that, but that's what causes that, and that's what happens. Then finally, this is the thing that combines the two. So we've got our tile pixels and our sprite pixels. Then this little bit of hardware does the actual sprite priority. And what it does is it determines if the sprite is going to be shown or if the tile gets shown, depending on that priority bit, if they overlap. And then this selects between tiles or sprites. And these are the 4 bits. And then this is the pallet number, because the lower 16 entries is tiles and the upper is sprites. So that signal goes into here, and it gets buffered along with which 4 pixels, and then our which pallet to use. And then that goes into our Pallet Ram, which is 64 locations, or sorry, 32 locations, 5 bits, 3, 4, 5. And then it has 8 bits for which pallet to show, and only 7 of them are used on the real system. It should be 6, and I'll get into that in a minute. And then here's our which pallet to use signal goes in here, and then that comes out and goes into bit 6. Yeah, bit 6 of our color ROMs. These are little 256 by 4 proms. And the data in them is repeated 4 times. So that means these A6 and 7 don't really do anything. And then, as you can see, this line isn't even hooked up at all. This is just floating in the breeze. So that means it'll pull high. So that means A7 is going to be high all the time. And then finally, we've got some resistors here. So this is our red, our green, and our blue. And on the real system, it's a 3-bit RGB, but blue only has 2 bits, as you can see. That's because these are 8 bits, 4 and 4. They would have needed a third ROM to get that one last bit. And they're like, well, you know, blue, humans suck at blue, so we're just not going to do it. And then there's this is part of the circuit on the board. There's a place for these 2 chips again, and these are the same Pallet Prams and the same RAMs. So I just drew it out. And then this chip, which drives them, is actually stuffed on the board, but it doesn't actually do anything. Those outputs don't go anywhere because these chips aren't on there, so I thought that was kind of funny. I mean, there was just a lot of really weird stuff. If we look at the inputs, here's all the gates that they didn't use. So, I mean, there's like enough inverters here for several more chips. So they could have eliminated chips. There's 8, 9, so there's 8, 16, 17, 18. There's 19 inverters. And since there's 6 per package, they could have got rid of 3 whole chips there and only had 1, you know, extra. 12 AND gates. So that's 3 more chips they could have just gotten rid of. Oh, I forgot about these inverters. No, I counted those, yeah. And then there's some NANDs they didn't use. There's only, what, 2? There's 4 NANDs. They could have got rid of another chip. They almost had enough to get rid of all these Xor gates. Yeah, there's almost 4 there. It looks like there's 1, 2, 3, 4, 5 OR gates. So that's another chip they could have got rid of. So they could have got rid of like 6 or 7 chips, but I don't know, the design seems very interesting that it was just kind of like slapped together, really. I mean, there's like lots of inputs that are not hooked up to anything. Like on this adder here, they didn't hook up inputs, you know, 2 and 3. You know, they're not using the outputs. They really didn't need to hook them up, but there's like, we're just not going to hook those up. But it's good practice to hook them up. Same here, they didn't hook them up here either. This 2002 read, you know, there's only 1 bit hooked up and all the others are just floating in the breeze. So that means these are all going to read high. So this will only ever return FF or it'll return BF. Yeah, BF. So it'll return FF or BF. I mean, the code ANDs it out. Actually, I think it uses a bit instruction, but I mean, that's just the way they did it. So when it reads 2002 and waits for bit 7 to be set, you know, to wait the 2 frames, well, it's going to be high because the input's not connected, so it'll just pass that check. I haven't looked in the code, but they probably didn't even hack that out. So yeah, that was very interesting look into this pirate board. So I hope you enjoy that. Like I said, there'll be a link to the schematic in the description. And maybe later on, I was thinking about actually putting an NSF on this board and actually have this thing play some NSFs to see how poor the Z80 like sound emulation is. I thought that'd be pretty funny. Thanks for watching. Hope you got something out of it.